So in today's lecture, we will discuss about linear approximation. For this, let us consider the graph of a particular function, which is f of x. We will consider a point on the graph at x equals to a. So its corresponding y value is going to be f of a. Then we draw a tangent line to the graph at this point. So this is our tangent line at the point P, whose coordinate is given by a and f of a. So what do we have to do in linear approximation is we'll use the equation of this tangent line to approximate the value of the curve at that particular point P. The value of this approximation is going to depend on the value of a, or how closer we are to a. Now if we use the equation of a straight line, that means if we use the point slope form, so the point slope form is given by y minus y1 equals to the slope of the function calculated at the point A times x minus x1. Then from our particular diagram, the equation of the tangent line will be y minus f of a, where f of a corresponds to the y coordinate of the point P, equals to the derivative of the curve calculated at the point x equals to a times x minus I. So y will be equals to f of a plus f prime a times x minus a. So here y we are going to approximate using the linear approximation function L of x. So this will be equals to f of a plus f prime of a times x minus a. So it will be using this equation to approximate the value of the curve at that particular point P. So let's try to do this with the help of an example. Problem number 1. Now using the method of linear approximation, let us try to approximate the value of 25.08. So to begin with, we can rewrite this particular expression square root of 25.08 as 25 plus 0.08. So here we will consider the value of a to be equivalent to 25 and the value 0.08 as delta x. Or we can also consider this to be the error in measurement. Now, if we look at this particular function, so this has a form f of x is equals to square root of x. So we can take its derivative with respect to x, and this is going to give us the value 1 over 2 times square root of x. And now that we have the value of fx and f prime of x, we can also calculate the value of this function at ax equals to 25, or a equals to 25 would mean the same thing. So we have square root of 25 and this value is 5, and f prime of 25 will be 1 over 2 times square root of 25, which is 1 over 10 or 0.1. Now that we have the value of f of a and f prime of 25, we can use the linear approximation function L of x, which is given by f of a plus f prime a multiplied to x minus a. So our f of a value is 5 plus f prime of a, which is 0.1 multiplied to x minus a here is 25. So this is our linear approximation function. So here we will take the value 25.08. So this will be 5 plus 0.1 multiplied to 25.08 minus 25. So that gives us 5 plus 0.1 times 0.08, which will be 5 plus 0.008 or 5.008. So this is a linear approximation. So we'll add square root of 25.08. So this is approximately equals to 5.008. So you can also use a calculator to verify whether if this value is correct or not. So you will see that when we take the square root of 25.08, so we get the value. This value is approximately 5.00799,361. So we can see we have obtained a pretty good approximation up to the 1000th place. So yeah, this is how we can use our linear approximation. So let's try to find out using the method of linear approximation. We want to approximate the value of 1 over 2.05. Here, we can rewrite 1 over 2.05 also as 1 divided by 2 plus 0.05. So here we are going to consider the value of a to be equals to 2 and 0.05. This was going to be the error. Now, if we look at our original value, which is 1 over 2.05, this has something of the form. The function can be represented as 1 over x. So we can use this particular function and take its derivative with respect to x to give us negative 1 over x squared. So here, if I have 1 over x, I can also rewrite it as x raised to the power of negative 1, and using the power rule, I get negative 1 over x squared. Now that we have fx and both f prime of x, we can calculate the value at f of a. So our a value is 2. So we have 1 over 2, which is 0.5, and f prime of a, so this will be negative 1 over 2 squared, which is negative 0.25. Now using this value, we can obtain our approximation function, the linear approximation function L of x, given by f calculated at 2 plus the slope calculated at 2 multiplied to x minus 2. F of 2 is 0.5. We have obtained it just now, and this is negative 0.25 multiplied to x minus 2. So this is our linear approximation function. Now what we want to do here, we will find the approximation for 2.05. So we have 0.5 minus 0.25 multiplied to 2.05 minus 2. So let's plug this value into a calculator, and this is going to give us 0.4875. So this is the approximation value of 1 over 2.05. And if we plug in the value of 1 divided by 2.05 into a calculator, so this gives us an approximation value of 0.4878. 0, 4. So if we compare the two results, we can see that our value is correct up to 3 decimal place. So it matches to 3 decimal place. So it's a very good approximation in the neighborhood of 2 because we have taken 0.05 here. Now tackle another problem. Let's say problem number 3. We have 8.07, and we want to find out the cube root of this particular value. What is the cube root of 8.07 is going to be using the method of linear approximation. So let us begin. So this can be also expressed as 8 plus 0.07 whole raised to the power of 1/3. Now we will consider that a is equals to 8 and our delta x going to be equals to 0.07. If we look at our original value, which is cube root of 8.07, this has a form cube root of x, or simply x raised to the power of 1/3. Now we'll take the derivative with respect to x, so this is going to be equals to 1 over 3 times x raised to the power of 1/3 minus 1, which is negative 2/3. So let's calculate the value of f of x and f prime of x at x at a equals to 8. So this will be f of 8. Actually, this is the value of x as well. So that's how we can calculate the value of f of 8. So this will be equals to 8 raised to the power of 1/3. That is the cube root of 8. This will be 2. And f prime of 8 will be equals to 1/3 of, so we have 8 raised to the power of negative 2/3. So this will be 1 over 3. 8 is 3, it's 2 cubed. So 2 cubed raised to the power of 2/3. So the 3 and 3 goes away because we need to multiply the exponent. So this will be 1/3 multiplied to 2 raised to the power of -2. So we have 2 squared, which is 4/4. So this will give us 1/12. So this is the value of f prime of. Now we'll try to obtain the value of a linear approximation function L of x, which is given by f calculated at x equals to 8 plus the slope calculated at x equals to 8 multiplied to x minus a. So f of 8, we obtained a value as 2. Then we have plus 1/12 multiplied to x minus 8. So this is a linear approximation function. Now we'll substitute the value of x with 8.07. So this will be 2 plus 1/12 multiplied to 8.07 minus 8. That's equals to 2 plus 1/12 multiplied to 0.07. And we have 2 plus 7 divided by 1200. So if we combine this, we have 2400. 7 divided by 1200. And this gives us a value 2.0058. And let's also try to find out the value of cube root of 8.07. So we have 8.07 raised to the power of 1/3. So this is giving us a value 2.005816. So here we see that we have our values which is very close to the original value because it's correct up to 4 decimal places. So this is a very good linear approximation that we have obtained. Let's move on to the next problem. Using the method of linear approximation, we need to approximate or estimate the value of natural log of 2.03. So let us begin. So we can express the given value as natural log of 2 plus 0.03. So here the value of a is equals to 2 and delta x, which is our error, that is 0.03. Now, if we look at log of 2.03, so this is f of x equals to natural log of x. Let's take its derivative with respect to x. This is going to give us 1/x. So we have f of x and f prime of x. So let's calculate the value at x equals to 2. So we have f of 2, which will be natural log of 2. And f prime of 2 will be 1/2. So using these two values, our linear approximation function will be given by, so f of 2 is natural log of 2 plus f prime of 2. So this value is half or 0.5 multiplied to x minus 2. So this is our approximation function. Now we'll calculate the approximation for 2.03. So that's natural log of 2 plus 0.5 multiplied to 2.03 minus 2. We have log of 2 plus 0.5 multiplied to 0.03. So we have log of 2 plus, we have 0.015, and this gives us a value. So we'll have to use the standard value of log. So this will give us 0.7081. And if we use a calculator to find a value of log of 2.03, so this is approximately 0.70803. So if we compare the two values, we see we have a value correct up to 3 decimal places. So let's do another problem. So here we have 1 plus x raised to the power of n, and we need to estimate its value or approximate it near x equals to 0. So let us begin. Here we have f of x given by 1 plus x raised to the power of n. If we take the derivative with respect to x, we have to use the power rule. So we have n times 1 plus x raised to the power of n minus 1. And using the chain rule, multiply it to the derivative of 1 plus x. So this gives us n times 1 plus x raised to the power of n minus 1. So this value will be equals to 1. So this is f prime of x. Now we have to calculate the value near x equals to 0. So that means near x equals to 0, or we can say at a equals to 0, f of 0 will be equals to 1 plus 0 raised to the power of n, which is equals to 1. And f prime of 0, this is equals to n times 1 plus 0 raised to the power of n minus 1, or simply n. Now let's use the approximation function. So we have L of x, which is given by f of 0 plus f prime of 0 multiplied to x minus 0. So this is equals to, so f of 0 we obtain, this is 1 plus f prime of 0, so this is n times x minus 0, which is x. So this is the approximation for 1 plus x raised to the power of n near 0. So this is how we can use the linear approximation function, which is actually the equation of the tangent line, to estimate the values of certain numbers.